Welcome to the presentation on top-down physical design of soft embedded FPGA fabrics. My name is Prashanth Mohan and I'm a PhD candidate at Carnegie Mellon University. Embedded FPGA fabrics are increasingly used in SoC designs as they offer a number of advantages including upgradability, feature addition, bug fixes, and security. eFPGAs are also used as accelerators in SoCs as they offer faster performance and lower power compared to CPU. eFPGA fabrics used in SoC fall into two categories, hard or soft fabric. Hard fabrics use custom layout techniques and are designed to maximize density, performance, and energy efficiency. But designing custom fabrics requires extensive time and effort, especially due to the increasing complexity of design in scaled technology nodes. Moreover, custom layout-based designs suffer from poor process portability as they must be redesigned for every new process technology. Therefore, hard fabric-based eFPGA designs are not compatible with tight SoC design schedules, budgets, and fab diversity needs. Soft eFPGA fabrics, on the other hand, are specified at the RTL level and can be synthesized using standard cells without any custom layout. Using standard cells and automatic place and route tools can reduce the architecture to layout turnaround times to less than a day and ensure excellent process portability. Therefore, soft eFPGA fabrics are more appropriate for use in SoC-based designs, especially with technology scaling. The primary challenge with synthesizing FPGA fabrics using ASIC EDA tools lies in the large number of combinational loops created by the highly interconnected nature of the FPGA fabric. EDA tools cannot optimize designs with combinational loops as they create cycles in the timing graph. Loops formed inside of a tile can be easily broken by specifying timing exceptions for the EDA tools, but intra-tile loops cannot be easily broken as they are spread throughout the fabric and can span multiple tiles. Previously proposed solutions to overcome this problem fall into two categories. One solution is to modify the structure of the routing fabric to remove any combinational loop in the circuit. But this solution trades off interconnect flexibility for synthesizability. An alternate approach to avoid modifications to the fabric is to use a bottom-up design methodology. In this approach, the intertile loops are avoided by synthesizing each unique tile separately and then stitching all the tiles together to create the full FPGA fabric. The problem with this bottom-up approach is that the tiles are optimized individually in isolation and there is no global timing view to optimize the channel wires that span multiple tiles. This problem has been alleviated to an extent by using manual buffering and floor planning to optimize longer channel wires. But these changes introduce significant deviations to the automated push-button ASIC place and route flows. In this paper, we propose a methodology to overcome these drawbacks. The top-down methodology has two main goals. The first goal is to eliminate the need for manual buffering and floor planning. The second goal is to enable a flat physical design flow to implement the whole fabric in one shot and avoid stitching multiple tiles together. We can achieve both these goals if we can break the intertile loops and create a global timing view for optimization. We achieve this global timing view by introducing a minor modification to the switchbox muxes. Each switchbox mux gets an input from the CLB that is highlighted in blue and the routing channels highlighted in green. In the modified mux, we separate the CLB and channel inputs and group them together on 2n boundaries that are defined by the mux select signals. We disable all the timing arcs via channel inputs and enable only the timing arcs via CLB inputs by using case analysis exceptions as highlighted in red. This technique can be used to optimize all the channel routes in the fabric while avoiding the formation of any combinational loop. We also use location agnostic clustering to reduce the delay through the channel inputs. Having global timing view enables flat one-shot implementation of the eFPGA fabric by using standard ASIC design flows while ensuring portability to any process technology with a standard cell library. We developed a fabric generator to implement the top-down methodology in silicon. Our fabric generation flow is based on Chisel hardware construction language from Berkeley and the VPR tool from University of Toronto. The input to the fabric generator is the VPR routing resource graph, which contains information about the routing resources and logic blocks present in the FPGA fabric. Our fabric generator reads in the routing resource graph and generates the modified switchbox muxes that are necessary for implementing the top-down methodology. It also integrates the logic blocks into the fabrics and adds the configuration cells required to program the FPGA as scan chains. It then dumps the Verilog description of the fabric along with the timing exceptions required for loop breaking as STA constraints. The Verilog and the STA constraints are then passed on to the physical design tools for implementation using standard ASIC design flow. In order to map the designs on the implemented fabric, we use a tool flow based on EOSIS and VPR. We also use our custom scripts to generate the bit streams from the VPR output files. This bit stream can then be used for formal verification and functional verification using Verilog simulations. We use this flow to implement FPGA fabrics using top-down design methodology and compare with bottom-up implementation. In order to compare the top-down and bottom-up methodology, we implement both these eFPGA fabrics on a 28nm industrial CMOS process. For our experiments, we use a 6x6 eFPGA fabric with 8 6-input LUTs per tile. The routing fabric has a channel width of 80 and a wire length of 4. The detailed VTR architecture parameters are shown in the figure on the right. All the experimental results are based on post-layout implementations. Since the goal of the top-down methodology is to eliminate the need for manual buffering and floor planning, we conduct trials to evaluate these two parameters. To study the impact of floor planning, we implement two versions of the design with and without floor planning. For the design with floor planning, we specify the placement locations of the tiles. For the design without floor planning, we let the timing constraints dictate the placement. Evaluating the impact of manual buffering is a bit harder because the results depend on the efficacy of the buffering strategy used. Therefore, we conduct two trials called bottom-up basic, indicated as BU, and bottom-up optimized, indicated as BU opt. In the BU trial, we let the tool fix design rule violations on longer parts that need manual buffering. This is representative of a low-effort buffering strategy. In the BU opt trial, we synthesize the design with a global timing view to insert the required buffers. We then place and route the fabric without the global timing view, similar to the bottom-up approach. This is representative of a fairly optimized buffering strategy. In total, we implement 6 trials to compare the two approaches as shown in the experimental matrix on the right. Now, let's take a look at the results. In order to compare the delay, we analyze the path delay histograms of the L4 paths in the FPGA fabric. Delay histograms provide an application-agnostic way of comparing and predicting the performance of the fabric. They also capture the extent of the delay variation across the L4 paths on the fabric. Ideally speaking, we need all the L4 paths in the fabric to have the same delay with minimum variation. We can see from the results on the right that the top-down histograms highlighted in red or plotted in red exhibit minimal delay variance. We can also see that floor planning has little to no effect on the L4 delay histograms for the top-down designs. Since the tool has a global timing view, it can place and size the cells automatically to meet the delay constraints without any issues, irrespective of the floor planning. We can also see that the histograms of both BU and BU op designs, which are highlighted in blue, green and blue respectively, show a large delay variance and have greater path delays compared to TD designs. This indicates that BU designs will perform worse compared to TD designs. Now let's take a look at the delay results of a few benchmark designs implemented on top-down and bottom-up fabrics to check if we see similar trends to that of the delay histogram results. On the right, you can see the critical path delays of various benchmarks implemented on top-down and bottom-up fabrics with and without floor planning. The critical path delays of the top-down designs, plotted in red, are approximately 15 to 20% lower than the BU op designs, plotted in blue. Moreover, the delays of the top-down designs with and without floor planning are almost the same. Therefore, we can conclude that floor planning is optional for top-down methodology and it does not affect performance. If we consider the bottom-up designs, the BU op designs marked in blue consistently perform better than the BU designs marked in green. Moreover, the BU without FP designs perform significantly worse compared to BU with FP designs. Therefore, we can see that floor planning improves performance, especially on BU fabrics. This shows that a manual buffering strategy must be carefully optimized for bottom-up designs. Another advantage of the top-down methodology is that we can optimize the fabric performance using a single clock delay constraint, just like a regular ASIC design. This delay constraint can be easily used to trade off area for delay and generate Pareto-optimal implementations of the fabric. The figure on the right shows the area delay trade-off in 28 nanometer technology node. We can see that there is a delay target window between 0.75 nanoseconds and 1.25 nanoseconds, wherein we can trade area and delay effectively. If the delay target is greater than 1.25 nanosecond, there is no significant reduction in area. Similarly, reducing the delay target below 0.75 nanoseconds incurs a large area penalty with minimal increase in delay. These plots can be obtained for different process technologies and architectures easily using the top-down methodology. With increase in compute and memory demands, heterogeneous fabrics with customized styles such as TSP and block RAMs are essential to implement a broad class of applications efficiently. But heterogeneity introduces irregularity, which complicates the bottom-up approach. For example, a fabric with TSP plus BRAM must implement 27 unique tiles in order to generate the bigger FPGA fabric. The size irregularity also complicates the manual buffering approach. Top-down designs simplify the implementation of heterogeneous fabrics as they can place and route the entire fabric as a single flat design, which is especially useful for integrating specialized custom fabrics into the SoC. Our fabric generator supports integrating custom tiles into the fabric to implement heterogeneous eFPGA fabrics. Specifically, we support custom tiles of various sizes in a column in 3 different formats. Hard micro tiles are supported for including logic blocks with custom layouts such as PRAMs, PLLs, etc. Soft micro tiles are supported for including macro blocks that are built using standard cells, and we also support tiles that are described in Verilog. To demonstrate this capability, we implemented a 12x12 heterogeneous soft eFPGA fabric with BRAMs as hard macros, CLBs as soft macros, and DSP as a Verilog. You can see the VPR architecture on the right along with the corresponding physical layout. We recently taped out this heterogeneous eFPGA using the Intel 22nm process. Compatibility with standard ASIC flow means that we can tightly mix eFPGA and ASIC at the RTL level. Such implementations have applications in logic obfuscation for hardware security. We demonstrate one such example by obfuscating the control logic of a 32-bit RISC-V processor and replacing it with a small eFPGA. The eFPGA has 16 CLBs with 124 4-input LUTs and 44 channels. Since this eFPGA fabric is going to be used only for implementing the control path of the RISC-V, we can use the bit stream to optimize the eFPGA for this specific application. This can increase the performance by up to 2x. For this implementation, the area and delay overhead was around 2x for a RISC-V running at 1 GHz. To validate the top-down design methodology, we fabricated a proof-of-concept soft eFPGA test chip which contains a 16x16 tile eFPGA with 2K 6-input LUTs. The eFPGA occupies a core area of around 1.74 mm². The eFPGA core is surrounded by FIFOs that are used for testing the eFPGA at speed. The eFPGA can be programmed by using a JTAG-like interface to load the configuration bitstream. The figure on the right shows the area and delay breakdown of the eFPGA test chip. About 8% of the area is occupied by the LUTs and the flip-flops. 50% of the area is occupied by routing muxes. 32% of the area is due to the 0.3 million configuration flip-flops that hold the configuration bitstream, and the remaining 10% is due to the hold buffers needed to fix hold violations on the configuration scan chains. As far as the delay breakdown goes, the LUT and the flip-flop delay accounts for about 1/3 of the total delay. The remaining 2/3 of the delay is due to the routing muxes. We evaluate the performance of the soft eFPGA test chip by using 4 different designs, which are 128-bit AES, a soft multiplier, a pipelined AES box, and a Sobel filter. The fully standard cell-based eFPGA can operate over a wide supply voltage range from 0.4 volts to 1 volt. The leakage power is also very low, ranging from 160 microwatt at 0.4 volts to 550 microwatt at 1 volt. The Schmo plot of the pipeline AES box shows that the fabric can operate up to 630 MHz when the design is heavily pipelined. We also compared the performance of our 16nm eFPGA test chip with Commercial FPGA Fabrics and show that our test chip performance is comparable to a 28nm Zinc FPGA and is about 2 to 3x lower than a 16nm Kintex FPGA. This difference is primarily due to the highly optimized custom layouts used in commercial FPGAs. Other factors contributing to increased delay include lack of architectural features such as carry chains, direct connections, and some inefficiencies associated with using open source toolflow. We propose a top-down design methodology for synthesizing soft eFPGA fabrics using standard ASIC flows without the need for any manual buffering or floor planning requirements that are associated with the bottom-up approach. Moreover, the top-down methodology provides tight delay guarantees and improved performance compared to bottom-up methodology. We developed a soft eFPGA fabric generator that is capable of generating eFPGA RTL and timing constraints from VPR architecture description. We showed that our design methodology is easily portable by designing fabrics in multiple process nodes. Our generator can also handle heterogeneous fabrics with block RAMs, DSPs, and other custom tiles. In order to validate our top-down methodology, we designed and taped out a proof-of-concept 16nm eFPGA with 2K 6-input LUTs. We showed that our eFPGA can run AES at 200 MHz and heavily pipelined designs up to 630 MHz. Future work involves open sourcing the fabric generator and integrating the soft eFPGA fabric into an SoC.